The first section in Chapter 4, we're going to talk about exponential functions. We've talked about multiple functions, and now this is going to be our fourth type. Now, an exponential function has the form y equals a times b to the x power. So as long as a isn't 0, because if it were 0, we wouldn't have a function. And the base b is a positive number other than 1. Because if it were 1, then it would just be constant, it wouldn't be exponential. So, if a is greater than 0 and b is greater than 1, then the function y equals ab to the x power is going to be exponential growth. And that value b is going to be your growth factor. So as long as b is greater than 1, that's what's going to make it a growth function. So what that means then, if a is greater than 0 but b is in between 0 and 1, so that means it's a fraction again. Again, we said we can tell so much just from that a out in front. So if a is a fraction, say 1/3 or 1/2 or 2/5, something between 0 and 1, then we're going to have an exponential decay function, and b is going to be the decay factor. So if b is greater than 1, we have growth, and if b is between 0 and 1, then it's going to be decay. So let's look at what they actually look like. So if you have a growth function, you're going to have b to the x where b is greater than 1. So just b to the x without an a in front of it, without anything being added or subtracted, just b to the power of x is going to be your parent function. And the reason we call this an exponential function, guys, is because your variable is part of the exponent. You guys have done functions where you've had exponents before, but you've never dealt with the variable or the letter x being part of the exponent. So the general shape for these is below. And what happens is you guys can see that as this graph goes from left to right, it goes away from your x-axis. So that's how you know that it's going to be a growth function. So for a growth function, as you go from left to right, your graph goes away from your asymptote. And that happens even if you guys have a negative value. So even if your graph is negative and it flips, it's still from left to right going to go away from your asymptote. And your asymptote, guys, we're going to talk a little more about this, but your asymptote is a line that your graph approaches but never actually reaches, because each time it gets closer and closer and closer, but it can't ever reach that. What happens is just your values, say your values get being cut in half. 1/2 can be cut into a fourth. A fourth can be cut into an eighth. An eighth can be cut into a 16th. You can cut that so small until you can't even see the values, but you're never going to be able to get to 0 because you're going to be able to keep making it smaller and smaller. So that's what an asymptote is. So for this one, your asymptote is your x-axis. And we draw an asymptote as a dashed line. So what happens is I'm going to say, okay, my asymptote is right here at x equals 0. That graph is approaching it, and it looks to us like it is touching it, but it's not ever actually reaching that value. So your graph should never cross your asymptote, that imaginary line that your function gets closer and closer and closer to. So your domain for these is going to be all real numbers. Remember, domain is left and right. Domain is your x value. So left and right. So your range is your y, and that's up and down. And what happens here is the range, guys, is affected by your asymptote. So if we start from the bottom and go up, the first place it's touching is going to be right there at your x-axis. So right here. So from there up is where your graph is. So that's why your range is from 0 on. So it has to be greater than 0. It doesn't touch 0. It is everything above 0. So again, once we start adding and subtracting things, it'll look a little different, but that is your parent function for an exponential growth. So now let's go down and look at the decay function. So again, decay means that your b has to be between 0 and 1. So, like 1/3, 1/2, 2/5, something between 0 and 1. So the general shape of your graph is below. Here, your asymptote is at 0 again because it hasn't moved. It hasn't moved up, right, left, any. It's just stationed there at your origin, at your x-axis. But for decay functions, if you guys look at this, as we move from the left to the right, it's approaching your asymptote. So for decay functions, as you move from left to right, your graph is going to approach your asymptote instead of go away from it. So again, because nothing has happened as far as adding or subtracting, your asymptote's at 0, and for this one, your domain is still all real numbers because it's talking about left and right. In the left direction and the right direction horizontally, in the x direction, there's no restrictions. There's nowhere that it stops or it's cut off. It just continuously goes in both of those directions. But the range, however, is still going to be in your vertical direction greater than 0. And we can write this in interval notation, guys, as 0 to positive infinity. Same thing here. And you can write all real numbers as negative infinity to positive infinity. So for exponential graphs or functions, your domain is always going to be negative infinity to positive infinity, but that range is going to be based off your asymptote. So let's go ahead and look at some examples, and then you guys can try some on your own.